Okay, good morning students. This is my 11th lecture and today we will be moving from first law of thermodynamics to second law of thermodynamics. So far we have done first law of thermodynamics for different category of thermodynamic activities, like for a closed system undergoing a process, for a closed system undergoing a cyclic process or cycle, and a thermodynamic activity through a steady flow device. So consequently we derived the steady flow energy equation and we saw how this steady flow energy equation can be used in solving thermodynamic problems involving devices like blower, compressor, etc. So in a subsequent class, I will also solve one or two more problems on that. Particularly, one problem is essential from the turbine side, and maybe one from nozzle and diffuser, because you get to know about what are the functionalities of these steady flow devices in thermodynamics or in actual engineering industries. Today we will discuss second law of thermodynamics. But before that, let us think what are the limitations of first law of thermodynamics. See, first law of thermodynamics, if you recall, says that if a process occurs, then Q is equal to W plus del U. Okay. Now think it in a very judicious manner, that if a process occurs, then process means thermodynamic process. If a process occurs, then Q is equal to total work done plus the change in internal energy. Now there is a if. Okay. So if that process doesn't occur, or if the first law is silent about whether the process will actually occur or not, about that first law is completely silent. First law only says, okay, in a process Q is equal to W plus del U, or in a cycle the net heat transfer is equal to net work transfer. But whether that cycle is actually doable, whether it is actually occurring, whether it is actually possible to occur, or if it is occurring, then what are the conditions under which it will occur, about that the first law is completely silent. Why I am telling this? Because an apple which is in the tree, on the branch of the tree, is having a potential energy mgh, and when it comes down and hits the ground, its total energy is half mv square, provided v is the velocity with which it will hit the ground. Now from simple physics and simple law of conservation of energy that mgh, the potential energy that the apple was having or possessing when it was sticking to the branch of the tree, is same as the kinetic energy of it when it will hit the ground. mgh is equal to half mv square. Okay. Now this is a process which everybody understands, and whenever you have done it in your school days or in your plus 2 days, the teacher must have given you this example that an apple is falling from tree, and this is mgh. This is here the total energy possessed by the apple is partly potential and partly kinetic, and when it hits the ground it is zero potential and all kinetic energy. But at every stage of its travel, the total energy of the apple remains constant. To explain you the law of conservation of energy, the teacher must have told you this example. Has any teacher given you an example that there was an apple lying on the ground, now suddenly the apple starts jumping and finally it stuck to the branch of the tree, and when it started with the velocity, its kinetic energy was half mv square, in the middle its potential energy this much, when it reaches the tree its potential energy is mgh. This example has anyone given? No, because everybody understands that apple falls from the tree spontaneously, but an apple lying on the ground spontaneously does not get lifted up, or doesn't start its motion suddenly spontaneously from the ground and gets to the branch from which it has fallen earlier. Okay, so an apple falling from tree is a spontaneous process, is naturally, it is thinkable, imaginable that it is falling from the tree. And the reverse of this process, that means an apple lying on the ground suddenly jumping and sticking to the branch of the tree is not occurable. Okay, is not normally occurring, is not occurring at all. Okay, in a as far as the natural phenomenon is concerned. Similarly, water is flowing from a height h1 to a height h2, where h1 is greater than h2, and everybody will believe it, water is falling from a or flowing from a higher altitude to a lower altitude, because this is a naturally occurring event, naturally occurring phenomenon. But and water, if I give you an example that water is flowing from the bottom of the hill to the top of the hill, okay, so immediately you will ask how it is flowing from bottom of the hill to the top of the hill, because you know that this is a process which is not naturally expected to occur. All right, so there are cases like this. For example, electricity flows from a point at higher potential to a point at lower potential, higher voltage to lower voltage, higher EMF point to a lower EMF point. So for everything to occur naturally, spontaneously, some force or some cause or some gradient or some kind of potential difference is required. That potential difference may be in the terms of electric potential, maybe in the term of height, maybe in the term of temperature. Alright, so all these things indicate that in nature certain directionality of processes are defined, and if anything is going to happen in the reverse direction, then it is against the law of nature, it is against spontaneity. So the process loses its spontaneity, or the spontaneous nature of the process is disturbed, because that doesn't happen in a natural way. Therefore, if you come to thermodynamics, thermodynamics says in a process heat transfer is Q, work transfer is W, change in internal energy U2 minus U1, then Q is equal to W plus U2 minus U1. But actually that process will occur naturally or not, about that first law is silent, because like any other natural process, thermodynamic processes, thermodynamic cycles also follow a directionality principle. They occur only in a particular direction and not spontaneously, and not in the reverse direction. That means heat is flowing from a high temperature body to a low temperature body. It is a natural phenomenon. Nobody denies it, nobody disbelieves it. Everybody believes that there is a hot body, there is a cold body. If you mix them together, then the cold body temperature will gradually shoot up, and the hot body temperature will gradually go down till they attain a common temperature or the state of thermal equilibrium. So this is understandable. But how do you explain that there is a cold body and there is a hot body, there is a cold region and there is a hot region, and heat is being drawn from cold region to hot region? And where does this happen? It happens in certain processes, it happen in certain cases. We'll come to that in the second law. So naturally that doesn't occur. Naturally there is a directionality which is to be followed, because it is natural or spontaneous. Second law now comes into picture, because first law is silent about this, that whether the cycle is possible or not, whether the process is possible or not. Second law comes into picture. Second law gives you clear direction. Second law says that this process will occur provided this condition is satisfied. This cycle will occur and give you work if this is possible. This process of transfer of heat from cold temperature to higher temperature will be possible provided you do this. So second law gives a condition under which the reverse process, which otherwise doesn't happen spontaneously or naturally, will happen, but with certain conditions. Now second law is there for a process and there for a cycle, but within the scope of your class we have only the second law applicable to a cycle only a thermodynamic cycle. So in this class we will be doing second law of thermodynamics, second law of thermodynamics, and we will be stating second law of thermodynamics in two different forms, or we will make two different statements of second law of thermodynamics. Both are statements of second law. One is named after Kelvin and Planck, the other one is named after a scientist called Clausius. So we will have a Kelvin-Planck statement, we will have a Clausius statement. Now Kelvin, what is I'm telling the difference between the two. Finally, ultimately you will come to know, or you will realize that at a higher stage you will realize that both the statements, although they appear to be different if you go by their words, but ultimately they speak of the same thing. But then we are not going to that in detail right now. We are trying to understand what a Kelvin-Planck statement is and what a Clausius statement is. Now Kelvin-Planck statement is all about a cyclic heat engine, and Clausius statement is about a cyclic refrigerator. First come Kelvin-Planck statement. Kelvin-Planck statement says that before you expect some work out of a cyclic device. Now tell me a device which will give you work. An engine gives you work. Okay, so Kelvin-Planck statement is all about an engine. So it says that if there is an engine and heat engine because an engine is called an heat engine if the input is in the form of heat. So your petrol engine, diesel engine, steam engine, they are all heat engines. Okay. Now we are giving some thermal energy as input and we are expecting and getting some work as the mechanical work as the output. Now from an engine what do we expect? We expect some mechanical work which we will utilize for displacing ourselves from one place to the other like an engine does. Okay. Now what does a car engine does? A car engine develops power or work that is used for shifting the body of the car from one place to the other on the road. That is what happens in case of an engine. So engine what it does? It operates in a cycle, that you have to remember that it operates in a cycle, because as long as we will continue our discussion on second law of thermodynamics, our discussion will only be confined to a cycle, because second law for a process we are not stating now. Actually that is not there in your course, but in one class I will tell what is second law for a process. But right now we are discussing second law of thermodynamics applicable for a thermodynamic cycle. Now that cycle, again we are taking a heat engine cycle and a refrigeration cycle, and in the heat engine cycle, in any cycle net heat transfer is equal to net work transfer. That means Q1 plus Q2 plus Q3 plus Q4 is equal to W1 plus W2 plus W3 W4. If you recall the first law of thermodynamics applicable for a cyclic process or cycle. But how actually this will happen? How actually when you give heat the cycle will give you work? That process, the sequence of events or the directionality of the processes that are prescribed by the second law and not by the first law. First law says if this is the work transfer, this is the heat transfer, both are same. But whether the heat transfer is fast or work transfer is fast, about that first law is not telling. Whether the work transfer will give rise to heat transfer or heat transfer will give rise to work transfer, about that first law is not telling anything. About that second law gives you a clear-cut prescription that if you have a cyclic heat engine and if you are expecting work out of it, then you have to supply heat in such a manner so that the engine will ultimately give you some positive work. Okay, so the statement is like this. You can write the statement. The statement says, Kelvin-Planck statement says that it is impossible it is impossible, it's a negative statement kind of thing, it is impossible for an engine, it is impossible for an engine operating in a cycle means thermodynamic cycle, to produce net work. It is not network, it is net work. Okay, so some resultant work, finite work, while exchanging heat between reservoirs at single fixed temperature. Don't worry if you don't understand this statement. I will explain it. Just remember it that second law says, Kelvin-Plank statement of second law says that it is impossible for an engine. Okay, so it is impossible to construct an engine. Write like this better. It is impossible to construct an engine operating in a cycle. This is very important because we are telling second law only for a cycle, so that engine must operate in a cycle, and engine does operate on the basis of a cycle. You might have heard that a diesel engine operates on the basis of a diesel cycle, a petrol engine operates on the basis of something called an Otto cycle, an aircraft engine works on the basis of a cycle called Brighton cycle. Similarly, a power plant operates on the Rankine cycle, and so on. So every power giving cyclic device operates on the basis of some basic cycle, and the cycles are named after the inventor. Now, such an engine operating on the basis operating in a cycle cannot produce net work if it will exchange heat between reservoirs at single fixed temperature. So there are negative things. That means it is impossible to construct while exchanging heat between reservoirs at single fixed temperature. That means if you can slightly change the wording to understand that it is impossible to construct an engine to produce net work if it exchanges heat between reservoirs at single fixed temperature. If it is exchanging heat between two reservoirs, reservoir means heat tank, you can say energy tank. That means from one tank the energy is coming, to another tank the energy is going. So one is called the source, from where the energy is drawn, and to the reservoir or to the tank where it is thrown, it's called the sink. And every engine works between a source and sink. Here what he is telling, that if the source and sink are at same temperature, then it is impossible for the engine to produce net work. That means if the source and sink are at different temperatures, then it is possible to produce some net work by the engine. Suppose I will tell you, if you don't give me 100 rupees, I am not going to give you this chocolate. Okay. So there are two negative phrase. If you don't give and I will not give. If you want to make a positive sentence, then you can say, what is the meaning of that sentence? If you give me 100 rupees, I will give you the chocolate. Okay. If you are not paying me 100 rupees, I am not going to give you the chocolate. That means if you are paying me 100 rupees, I am going to give you the chocolate. Similarly, it is impossible to construct an engine to produce net work if it is exchanging heat between source and sink at same temperature. That means if it is exchanging heat between source and sink at different temperatures, it is possible to produce network. That's the meaning of it. And it will be more clear if I draw the schematic diagram now. Okay. So, the second law says it is impossible to construct an engine operating in a cycle to produce net work while exchanging heat between reservoirs at same temperature. Now let us try to understand what exactly it means. Now this is a reservoir, means it is a tank. Just like a water tank, this is a thermal energy tank. Okay. Let us say this temperature is T1 and this temperature is T2 and the engine is in between and engine is working between this reservoir, which is the source, and this reservoir, which is the sink. Source and sink. Okay, temperature is T2, temperature is T1 here. And some heat is coming, you can get work only when some energy is spent. Now, how can the engine give you work? Only when it utilizes some heat or energy from some source. So it is extracting some thermal energy from source. Let that amount be Q1, and this Q1 is coming from the source to the engine and it is giving you some work. So if you look at this, then how many reservoirs are there? How many reservoirs are there? There is only one reservoir, which is source. So heat is coming from the source and engine is doing some work. According to second law of thermodynamics, this is not possible. Second law, according to first law, it is fine. First law says, okay, Q1 amount of heat is coming, W amount of work is done, Q is a form of energy, W is a form of energy, and Q is equal to W. Energy balance holds good. First law will tell like this, but that is limited. That is the limitation of first law. First law cannot guarantee you the production of work simply by transfer of heat from source to engine. It is only the second law which clearly defines and pinpoints and puts the condition that if you want to get W amount of work from Q1 amount of heat, then one reservoir, the source only, cannot do. You have to have a sink and the engine has to interact with the sink with amount Q2. And not only that, the source and sink, the heat reservoir from which heat is drawn and the reservoir to which it is given by the engine and to the engine, cannot be at single fixed temperature. That means T1 cannot be equal to T2. So heat flow is taking in this direction. If it is a natural flow of heat, obviously this will be a high temperature regime and this will be a low temperature regime. So T1 is greater than T2. T1 is greater than T2. T1 is equal to T2, no work done. First law, the second law says, Kelvin-Plank statement says that the engine is not going to produce any network if the reservoirs are exchanging heat at single fixed temperature. So this is the schematic of a heat engine. The heat engine, the diagram says that for a heat engine to produce work, and what is heat engine? Heat engine is a cyclic device. It operates on the basis of a cycle, and meaning of being operated on the basis of a cycle means the working substance of the engine. मतलब जो engine का अंदर जो working substance, if it is a petrol engine, air petrol mixture, if it is a diesel engine, diesel and air mixture, that are getting circulated within the engine has to undergo a change of state in such a manner that the initial and final states are same, going by the definition of thermodynamic cycle. And in that case only the work output is possible. So it is very clear that second law states that if there is a cyclic engine and if you want work output from the engine, then two things are to be satisfied. First of all, the engine has to operate between two reservoirs, not one, and the two reservoirs called source and sink, depending on whether heat is drawn or whether heat is thrown, have to be at two different temperatures and not at single fixed temperature. they have to be different. So first is that it is to operate on the basis of a cycle. It must be a cyclic activity. Second is that there must be two reservoirs, and third thing is that the two reservoirs must be at two different temperatures, not at same temperature. Only in that condition the spontaneous process is possible, natural process is possible, and you get some work. Now you apply first law. सेकंड लॉ अभी बोल दिया कि ये कंडीशन है, ये कंडीशन सेटिस्फाई करोगे तो तुमको वर्क मिलेगा. अभी हम देखेंगे कितना वर्क मिलेगा, कहां से मिलेगा. नाउ यू कैन अप्लाई फर्स्ट लॉ, बिकॉज फर्स्ट लॉ इज, when we are discussing second law, does not mean that first law is invalid. In this concept first law also has to hold good. So first law यहाँ apply करते हैं. So this is the engine. Now this is the engine. What is coming to the engine is Q1 is a amount of heat that is coming to the engine. Q2 is the amount of heat that is rejected by the engine. One is supplied to the engine, one is rejected by the engine. So what is the net heat transfer to the engine? Q1 minus Q2. And what is the net work transfer? The W. So this W and Q1 and Q2, there must be a relationship between, or there must be a relationship linking W and Q1 minus Q1 and Q2, and the internal energy term is not there altogether, because we are talking of an engine which is operating in a cycle. And we know, if you recall if you connect it to the what we discussed in the first law, in a cycle the internal energy being a point function vanishes from the final equation. It vanishes from the final equation. Only net heat transfer is equal to net work transfer. So what is the net heat transfer here? Net heat transfer is Q1 and Q2, one of them is plus, one of them is minus. Which one is plus, which one is minus? Or if you take this as the system, then what are the energy input? Q1. What is the energy output? W. And what is the heat going out? So W is Q1 minus Q2. W is Q1 minus Q2. This particular thing speaks of many things. Like for example, it says that whole of Q1 which is coming from source at temperature T1 is not getting converted to work. Only a portion of that W is getting converted to work. The remaining portion is rejected by the engine. And the rejection is a must. If you don't reject, you don't get work. So Q2 cannot be 0. Because if Q2 is 0, that means the existence of sink is not there, and according to second law, a sink has to exist, a source has to exist, a sink has to exist, and engine has to work in between source and sink. The engine has to draw some heat Q1 and it has to throw some heat Q2, and the difference of Q1 and Q2, only the difference of Q1 and Q2 will appear as mechanical useful work output. So whole of Q1 is not getting converted to W in a cyclic process or in a heat engine. That is the story, that is the main essence of second law. Whereas अगर यहाँ फर्स्ट लॉ होता, फर्स्ट लॉ बोलता कि अगर हीट Q amount of heat is given, okay, Q and W are same thing, energy, total energy cannot be created nor be destroyed. So Q is equal to W. But that is not possible in nature, it is not practicable. The practicable limits and practicable conditions are prescribed only by the second law. Okay, so this is the Kelvin-Plank statement of second law. In the next class, we will try to understand what are the inferences that we can draw from Kelvin-Plank statement, and from that how we will know that what will be the efficiency of engine, and what is the efficiency that an engine cannot reach. So all these things we will infer from the second law of thermodynamics Kelvin-Plank statement in the next class. And after understanding that, we will move to the second statement, that is Clausius statement, which speaks about another class of device, not engine, another class of device, cyclic device again, called refrigerator. Okay, This much for today. Thank you.